Hi, I'm Steve Weintraub. It's my honor and pleasure to introduce the speakers for this morning's lecture. The first lecture today is going to be given by Eamonn O'Brien. Eamonn received his PhD from the ANU in Canberra, then was a research fellow there, and has been at the University of Auckland since 1997, at least logically, though physically he just returned from a Humboldt fellowship in Germany, just in time to give his talk, which will be on effective algorithms for linear groups, successes and challenges.
Okay, good morning everybody. It's such a pleasure to give a lecture to a large group of people. At the University of Auckland, we sometimes give lectures to much more select audiences, which often reduce to about 20 as the semester goes on. Of course, as the first speaker, I have the advantage that so many people are captive for at least a little while. Let me thank Stephen and Bernd for the introduction, and also let me record my thanks to the organizing committee for the privilege to give a lecture here. It's a great privilege to have the opportunity to be part of such a large meeting. And in that respect, I also want to acknowledge on my own behalf and that of all of the participants, the work of Melissa and her outstanding team of people to ensure that 850 people are here. Okay, the topic of my talk is on aspects of linear groups. For people who don't know me, I'm a computational group theorist, so a lot of what I'm going to be focusing on is on particular computational aspects, algorithmic aspects. I should begin by stating that I'm trying to survey something which has an ongoing project of 30 years duration. So if your name is omitted, my apologies at this instance for doing so, because there's a finite number of people whom I can mention during this talk. I'm starting life with a subgroup of invertible matrices with entries from GFQ. A little bit towards the end of my talk, I'll try to switch to a more general context, but now I'm taking D by D matrices. I have a generating set, capital X, which describes the group. It's almost a theorem that any interesting group is generated by two elements. So don't get carried away with X growing. X is nice and small and doesn't play any particular role in terms of the complexity of the resulting algorithms. As a group theorist, or even as somebody who uses representation theory, what you're going to be interested in are a bunch of natural questions, such as the group is a subgroup of GLDQ, therefore of necessity it's finite. I'm interested in knowing what the order of the group is. I'm interested in knowing composition factors, which loosely are regarded as the building blocks. An inappropriate analogy is that we think of them as the equivalent of prime factors, but sadly they don't commute. So lots of nasty problems occur when we try to build groups from equivalent composition factors. And then there's a bunch of information which we're interested in about the structure of the group, such as P-group structure or Zelo subgroup structure, knowing something about conjugacy classes of elements. I'll mention a few more as we go along. And as I said, I'm a computational group theorist at heart. A lot of what I do is developing and implementing and applying algorithms to answer problems. And so I'm interested in both the theoretical and practical efficiency of algorithms. I'm going to mention that, of course, one measure of efficiency is the complexity in terms of the size of the input. Our input here consists of D by D matrices, so D squared entries, each of which requires log Q bits. So in effect, the input size is D squared log Q. I'm interested in algorithms which run in time polynomial in those parameters. In particular, I am not interested in parameters involving Q, partly because the question of efficiency just kills us in practical terms. Okay, so let me begin with an easier context. Let me look at this situation if I want to answer those questions for permutation groups. And here, of course, the name which must be mentioned is Charles Sims, who died very recently, made incredibly important contributions in the late 60s and early 1970s in developing the concept of base and strong generating set. I'm thinking of a permutation group acting on a finite set. I'm thinking of having a bunch of points which I label epsilon 1 to epsilon m from this set omega, and I'm demanding that the stabilizer of each point in that set is equal to the identity. So the only element which fixes every point in that set is the identity element. And that's what we call a base. And if we have a base, then we can use very standard almost graduate level techniques in order to build up a chain of subgroups. The first thing we use is what we call the orbit stabilizer theorem, which tells us that if we want to construct the stabilizer of a point, then what we're really interested in is knowing about the orbit of that point under the action of the group. So the orbit stabilizer theorem says to us that the index of the stabilizer, what I call G epsilon 1 here, is actually of index R1, where R1 is the cardinality of the orbit. And I can iterate this procedure by taking, within G epsilon 1, I can take the stabilizer of point epsilon 2, repeat the process. And because I've chosen a base, I get down to the identity at the end of it. So I've produced a chain of subgroups. And that chain turns out to be incredibly significant. The base I've already mentioned. The strong generators correspond to the use of Schreier's lemma, if you're familiar with that, for the purpose of writing down the generators of the stabilizer. Okay, so at the end of this, I can answer at least one question immediately. I can tell you what the order of the group is. It's the product of the sizes of the orbits. That idea, which was developed and proposed by Charles Sims at the end of the 1960s, has been fundamental in terms of working computationally and effectively and theoretically with permutation groups. The idea, the algorithm itself is complexity O(n) to the fifth. That statement depends heavily on what data structure you're using, how much space you're willing to commit, but effectively, it's a nice polynomial, fairly small degree polynomial. Eugene Lux in the 1980s, 1987, used this idea as the foundation for an algorithm which gives you, in polynomial time, the composition factors of a permutation group. And as I said, many other algorithms have since been built on that. Names to think of: Bill Cantor, Akal Sherries, a whole host of people have contributed in terms of exploiting this chain of subgroups and using it as a good tool for working with permutation groups, both theoretically and practically. Okay, so first natural question you might ask is, why don't you do the same thing in the context of matrix groups? We have a group acting on a vector space. We have a very natural action. I'm thinking of the matrix acting on the right, multiplying the vector to give us a new vector. And so we can talk about an action, and we can write down a base for the group. Typically, the base could consist of just standard basis vectors. You might be more clever and take subspaces of various dimensions, but in practice, you can try to do that. Okay, and in fact, that was done by Greg Butler in the 1970s. Fairly soon after Schreier-Sims was introduced, it was developed. It has a central problem, namely, good subgroup chains along the lines which I introduced for the purpose of permutation groups need not exist. As an example, if you take J4, which is a very famous, much-loved sporadic group, it has a representation of dimension 112 over GF2, and its best permutation representation has this degree, 173 million. In practice, there are people in the audience, including me, who are happy to work with 173 million degree permutation groups, but it's not what you will do on your little laptop, by the way. You need to think about it pretty carefully. Okay, and the central difference, I just want to point out what the central difference is between permutation and matrix groups, which means that Schreier-Sims as an approach is doomed to failure for large degree matrix groups. It is, within Sn, you've got a very natural occurring subgroup, which is Sn minus 1, which is indexed precisely n inside of Sn. That gives you, in effect, a nice chain of subgroups. You take the analogous situation for GLDQ. You take a stabilizer of a maximum, or you take a maximal parabolic within it. And what's the index? The index is now q to the d. Your input, remember, is d squared log q. If you follow this approach, you're already failing on complexity grounds. In practice, Schreier-Sims for matrix groups remains a good tool to use, but it's limited. Think of D being about 8, think of Q being about 7. That gives you an idea of where the upper bound is. And that realization is what led almost, essentially 30 years ago, to people looking for new techniques to work with them. And before I talk about that, I want to just point out something about the nature of the algorithms which come out of what is loosely called the Matrix Group Recognition Project. First of all, to give you an idea, GLDQ is a big group. Its order is of big O of q to the d squared. So it's not small, and you've got to bear that in mind. That has an impact that most algorithms are not deterministic for working with such groups. They actually exploit random elements. I could give an entire lecture series on the subject of random elements. Suffice to say, they're a good practical and good theoretical understanding of how we construct random elements, and in practice, we can do it quite efficiently. And the algorithms that I'm going to be talking about make use of the ability to construct random elements. Okay, within the context of randomized algorithms, there are two broad classes, the first of which is called Monte Carlo. Monte Carlo algorithms, some mathematicians are unhappy about because they occasionally lie. They lie with a small probability which can be reduced still further by doing more work. If the user wants to do more work, you can reduce the probability of error. And then there, of course, there is a much better American version called Las Vegas algorithms. And Las Vegas algorithms don't lie, but they have a nasty problem that they could run forever. There are various ways of addressing that at a theoretical level, but suffice to say, the algorithms I'm talking about fit within this framework. We want, where possible, to have Las Vegas algorithms, which don't tell us lies. Okay, I'm going to tell a number of lies today, by the way, but that's in order to make some of this sound coherent. Okay, very important in terms of analysis of algorithms is that we have this relatively recently developed field of statistical group theory. There are a number of pioneers whom I want to particularly single out, two in particular, Sherp Prager and Elise Niemeyer, and many of their collaborators have worked on providing enormously accurate, detailed analysis of the proportion of elements which satisfy particular conditions. If you want something to hang on to, if I give you a matrix and I ask whether its characteristic polynomial has a single factor of degree 1, and the rest of it is a single factor of degree d minus 1. What's the proportion of elements within a classical group which has that? That's the sort of question, and they give you really incredibly precise. They're not O of d to the log, they're very, very precise estimates, which actually are realized in practice. The algorithms which I'm talking about, most of them will deal with so-called natural representation. For the non-group theorists, if you want natural representation, think of the special linear group of degree 8 over GF5. I'm talking about 8 by 8 matrices of determinant 1 given with entries from GF5. That's what a natural representation is for me and for the purpose of this talk. But there is a class, a broad class called black box, which in some sense consists of tying your hand behind your back and saying, I'm going to make no use whatsoever of the structure or the representation that I'm given. I'm instead going to use only group axioms. So I can multiply elements, I can invert, I can check whether something equals the identity, nothing more. I'm not going to make any use of the fact that I've got a matrix or permutation to help me along the way. And what has often happened is that algorithms start out being black box, and then we turn them into natural representation algorithms by throwing away the hard parts and ending up with something where we can make use of nice features of the representation. Okay, so back in the early 1990s, Sherp Prager and Peter Neumann suggested exploiting Aschbacher's classification of maximal subgroups of classical groups. I've already mentioned one classical group to hang on to, SLDQ, for example, invertible D by D matrices of determinant 1. Okay. What does Aschbacher state, or what does my version of Aschbacher state? This is a 100-page paper in Invenzioni, so my version of it is what's suitable for 30 seconds here, so please bear with me. The first thing is to say that either we have one of two situations. Either G, which is given to us by collection of matrices, preserves some nice natural linear structure, and there's a normal subgroup associated with that natural linear structure, or we're in the situation where G is almost simple modular scalars. Close to being simple, not quite. The fact is that it's modulo its center, it sits inside the automorphism group of a simple group. But for all intents and purposes, we've got this binary classification, and that led to a proposal along the following lines. There are 9 Aschbacher categories, and I'll talk a little bit about those in a few minutes. But it says as a strategy for working with linear groups, forget about Schreier-Sims, instead determine at least one of these categories, and if there's a normal subgroup, make use of the normal subgroup. And I've put solve in inverted commas. I'm saying take the normal subgroup and work with the normal subgroup, take the factor group, work with the factor group, and ultimately refine to get down to a composition series. If you have a composition series for the group, it gives you a great deal of insight into the structure of the group. Okay, so let me look at one of the cases. These cases are typically called C1 up to C9. Sometimes a C9 becomes an S, depending on who you are. I'm going to stay with C2. C2 being one of these cases where the group acts imprimatively on the underlying vector space. So in other words, the space is written as a direct sum, and those summands are being permuted. So where do you get a homomorphism from this, from G to the symmetric group of degree R, where R divides D, and the normal subgroup arises very naturally as the kernel of this homomorphism. I've illustrated it here. I'm going to stay with this notion of illustration in terms of writing something on the right as the image of a homomorphism, and something on the left as being the kernel of a homomorphism. And my first foray into this topic was back in 1996 when Derek Holt, Charles Leadham Green, who's been my long-term collaborator on almost everything that I'm talking about, and Sarah Rees and I developed a polynomial time algorithm which decides membership in the C2 class. In other words, it produces this particular decomposition, it produces the homomorphism and allows us to do a recursive strategy. Okay, next transparency is for the experts. Forget if you haven't an interest in what the classes are, don't worry too much about it. What I've listed here are the 9 classes in Ashbacher. Where there's a yes, it says, yes, we have a nice polynomial time algorithm which answers the question. The first one, by the way, reducible, it just means there's a nice subspace of the vector space which is fixed under the action of the group. And that allows us to write down the action on that subspace, hence producing the image, and we can talk about the kernel to that. The reds correspond to 2 cases where we do not have a polynomial time algorithm to answer the question. We do have eminently practical algorithms which answer the question, but we have not been able to prove that they run in polynomial time. So if you have excellent students who need a nice challenge, these are the 2 cases we'd love to get input on. I'll come down and talk about C8 and C9 later. C1 to C7 give us a natural action and give us a normal subgroup. Okay, so here's the first long list of names. I'm not going to even read them out, apart from perhaps to identify Peter Brooksbank, who's contributed a great deal and who happens to be here. I don't think there's anybody else here, so I won't offend them by not mentioning their names. But there's lots of people who've contributed, and the resulting practical algorithms are available in Magma, can be used very well. Okay, a byproduct for people who know about Clifford theory, you get a polynomial time version of Clifford's algorithm, or Clifford's theorem. Okay, so coming back to the general strategy which we have, the first 2 pieces I've talked about, otherwise we're in this C8 and C9 category. C8 is groups, classical groups and natural representation, and C9 is the bin consisting of everything else. For experts, cross-characteristic representation, non-natural representation, anything that's not occurring as a tensor product will turn up in this bin. Almost all interesting groups turn up in this bin. Why do we separate off C8 and C9? C8, beautiful groups, we love them, they're nice representations, they're doubly infinite in the sense that D and Q both go to infinity. C9, there are results which say the orders of groups in C9 are much smaller than Q to the D squared. They're literally about Q to the D. So they're much smaller, much better behaved, but they're very hard to work with. Okay, and so what the next part of the strategy is to reduce from G to a quasi-simple group. Quasi-simple group is a perfect group which modulo its center is simple. So it's again close to being simple. The reduction is very easy. We simply take derived groups, which we could do from a theoretical point of view in polynomial time. Naming L. What do I mean by naming? I actually want to know what the group is. I don't mean I want an isomorphism at this stage to a nice copy. I just want to know, is it SL85 or is it J4? Depending on which it is, I want to apply very different strategies. And the last part of it is, I want to set up constructive isomorphism between L and its standard copy. If I'm given some tensor power of SL85, the standard copy will be SL85. And I want to have maps which allow me to go between the nasty copy, which has been produced as an element of the class C9, and the standard copy. Okay, I'll come back to this last point, and it will form much of the last part of my talk. But first of all, I want to talk about the naming part. And I'll do this in 2 stages. One is to talk about deciding membership in C8, which was classical groups and natural representation. So here I'm talking about, given a bunch of matrices, do they contain a quasi-simple group? So SL, SP, SU, orthogonal groups, that's what I want to know. Does this group contain such a group? And the original motivation came from Neubusser in 1988, who asked whether or not there's an algorithm which decides whether or not, an analog of the algorithm which decides whether or not a subgroup of the permutation group contains AN. Part of the reason for that is that AN and SN have long bases. Essentially all other subgroups have short bases. That influences the performance of Schreier sims, so you're interested in being able to decide quickly whether you're in the situation of having AN or SN versus something else. Okay, and there's beautiful work of Prager and Neumann from 1992 and Prager and Niemeyer from 1998, which says to us there are indeed polynomial time algorithms which can decide very efficiently indeed whether or not a given group contains a classical group in its natural representation. I draw your attention to O log D. That's the number of random elements. If you want something to keep yourself busy for the next 20 minutes, try finding a D where that value exceeds 5. What's going on? What's going on is very simple notion of primitive prime divisors. I've defined it here. A primitive prime divisor R is a primitive prime divisor of p to the e minus 1 if it doesn't divide p to the I minus 1 for 1 less than or equal to I strictly less than e. And we have a notion of PPD elements, which are elements whose order is a multiple of some primitive prime divisor. Think about if you're an expert, you already know what the order of classical groups are. They involve lots of powers of the form p to the e, I minus 1, etc., and powers of p. So that explains to you why there are many elements which are indeed PPD elements. And what, in the very brief summary of Prager et al. Would say, most subgroups of GL which contain primitive prime divisor elements of a very specific kind actually are classical groups or contain classical groups. And they give you very good algorithms to find such elements and to eliminate the few cases which are special. Okay, so that algorithm is very important. We're interested in not just being able to name C8, but we're interested in also being able to name the groups such as a tensor power of SL85. How do I do that? I use this variation by Babai et al. From 2002, which says to us, given a group where I'm not paying attention to the nature of the representation, can I determine its name, its standard name? And indeed, subject to the known characteristic, you can compute its standard name. It's using so-called Artin invariants for the experts, again a variation of PPD elements to get this result. And that's a very practical, realizable algorithm. This is the known characteristic. We need to know, is SL85, we were given it in characteristic 31, for example. We need to know what its defining characteristic is as input. And there's an algorithm of mine with Martin Liebeck, which answers that question again within the same context, subject to the existence of an order oracle for answering the question, what's the order of an element? And if you're very keen on that topic, come to my second talk tomorrow afternoon as part of the computational number theory, where I'm actually talking about aspects of that. Okay, so we can name the group, and that helps immensely for what I want to do, which is to talk about constructive recognition. In summary, constructive recognition sets up an isomorphism between the standard copy of a group and the user-supplied copy or the version which came out of application of Aschbacher. And so the world is that we're given C with some generating set where C is quasi-simple. I think of C being the standard copy, so SL85 is 8 by 8 matrices over GF5. That's what my standard copy is. And now some nasty person comes along and gives me a group. And by use of the naming algorithms, I decide that it's isomorphic to SL85. For the experts, yes, I'm avoiding questions of the center. Don't worry about it. We have to take care of it. But for this purpose, I'm just asserting an isomorphism involving between G and C. Note, I am deliberately using X and Y. There is no relationship between the generating sets. If there was, this problem would be trivial. But we don't know that. And I want to construct effective isomorphism going both directions. If you're a non-computational group theorist, you may well think isomorphisms, of course, go both ways. But I actually want to be able to move between G and C. So I want effective isomorphism in both directions. Here's a key requirement. I want to solve the membership problem. Membership, I'm given G as a subgroup of some linear group. I take an element of GLDQ and I ask, does that element lie in G? If it does, I want to know what the word is in terms of the generator's Y. That's absolutely fundamental to answering questions which I will use for applications later. And the key idea is to use standard generators in both C and G to write down a isomorphism. Okay, let me try to illustrate that. Here's my gold copy. I don't think that's very gold. I think it's very orange rather than gold, but that was my best attempt using LaTeX to produce this. So let's take C with a generating set X. Here's my G sitting over here with a generating set Y, and I'm going to tell you what I want to do. I want to find standard generators in C as words in X. And I want to find standard generators, which I've labeled S bar, as words in Y. And now I can define my isomorphism by extension from the generating sets. Okay. That's what I would like to do as one part of it. I also want effective means of going between C and G. How do I achieve that? Suppose I take little h sitting over here, and now I'm writing h as a word in S in the standard generators. I'm not trying to write it as a word in some arbitrary, nasty generating set called X. I'm writing it as a word in S, and that's a much easier task. And of course, I know that as a word in X by just doing substitution. And then I can take h bar, write down h bar over here by just evaluating, by substituting for S and S bar. Okay, that's how we go from C to G. And to go back, it's the same thing, provided I can write h bar as a word in S, then I can evaluate what its image is back in C. Okay, very desirable, clearly, but I haven't told you anything about how it's done. All I've done is to identify tasks. If I could do these, I would indeed have all of the necessary machinery. Okay, so here's the outcome. And I tried to put the list of names in small to ensure that nobody could read anybody's name on this list, but unfortunately it failed. In any case, let me first of all tell you what the statement says, and I'll focus on parts of it. So, given a group G with the generating set Y, I want to find standard generators S for G as words in Y. And I'm claiming there's a Las Vegas algorithm which takes as input G and returns that. And for all but a short list of exceptions, the algorithm runs in time polynomial in the size of the input. What's the complexity? The complexity is R to the 4th log Q, where R I'm using as the rank of the group of Lie type. So this is a statement about groups of Lie type principally, but versions of it exist for all finite simple groups. Okay, huge list of people here who have contributed to this. Peter Brooksbank again, Bill Cantor, Charles Prager, Heiko Dietrich, Henrik Barnheim, Martin Liebeck, and of course Charles Leland Green, whom I mentioned earlier, and without whom almost none of these ideas would ever have come to fruition. Okay, what are the, I've also stated that subject to discrete log and factorization oracles. I'll again be discussing that tomorrow afternoon. So that's my second advertisement. Okay, exceptions. What are the exceptions for the experts? They're the exceptions. Three infinite families in one direction for Q. Defined typically over fields of characteristic 2. There's a good reason for that, which I'll be happy to share with experts later. Say a few words about it. Recursive algorithms. The algorithms which I've been involved in are highly recursive. We start out with some representation G, which is given to you in dimension 100. We come hurtling down as quickly as we possibly can to produce nice small groups in which we can work effectively. The most common group that we produce is SL2Q. So 2 by 2 matrices defined over GFQ. You might well think that everything about SL2 is easy. I can assure you it's far from it. If you deal with SL2, then the other base cases for recursion typically turn out to be omega 4 plus, which is another horrible group for, as far as I'm concerned, from a practical point of view. Okay, key to centralizers or key to exceptional groups and classical groups are centralizers of involutions. Of course, people who've worked on finite simple groups are fully aware of the critical importance that centralizers of involutions played in classification work. For at least 40 years, they've also been used extensively for computational work. That mostly dates back to the work on the Atlas at Cambridge in the 1980s, formalized by John Bray in a very beautiful paper in 2001, where he gives you a method which exploits properties of the dihedral group in order to construct random elements of the centralizer of an involution. There are results which tell you that if you have a small bounded number of random elements of a centralizer, that you have the full centralizer, so-called generation properties. In odd characteristic, if you take the centralizer of an involution, you take the derived group of the centralizer, then what do you get? You get a direct product of classical groups in smaller dimension. That's how the recursion operates. We start out by taking a centralizer of an involution, we come down to the derived group, we extract SL4 inside of SL8, and now we do the same game again to come down to SL2. So that's a very brief sketch of what goes on in this context. Where do these exceptions come from? The exceptions come because we cannot prove that we can find an involution within those groups in polynomial time. I'd love somebody else to give us a method of finding an involution in polynomial time within such a group. I also want to go back to this complexity for one moment to say it's quite staggering, because if you think about what the cost of matrix multiplication is, it's d cubed using standard algorithm. We're saying that in d to the fourth, we're able to establish the necessary machinery to have an isomorphism between any nasty copy of a group and its standard copy. Okay, all right. One word which I didn't focus on here was Las Vegas, so therefore I'm certifying that I have an isomorphism. So far, all I've done is produce something which I assert is an isomorphism. In order to verify that I've got an isomorphism, I want to make use of presentations. And there's, in this context, work which is not strictly relevant, which I really do want to draw your attention to, which is very beautiful work of Goralnik et al., Alexander Holke et al., which included James Wilson and Martin Kassaboff and the late Akash Sherez, which gives you the following statement, that every finite simple group of Lie type of rank R defined over GFQ has a presentation of length, log Q plus log R. That's an astonishing statement in the sense that input to such a procedure is actually the value R. And you require log R bits to represent it. And we're saying we literally write down a presentation where if you count the number of symbols, it fits into this framework. Sadly, those presentations are not on standard generators. We want them on standard generators. And so Charles Leadham Green and I spent something like 15 years of very stressful work trying to write down presentations on standard generators. And here we get, there's at most 8 standard generators. These are quite explicit presentations which we make use of at a machine level, and they're on the standard generators. Note the difference in the length, log R plus log Q versus R plus log Q. Where R, if you're worried about it, think of just the dimension of the matrices. In fact, it's much smaller than that. Why the difference? The difference is, again for the experts, I want to deal with file groups. AN and SN turn up. If I want to deal with SN, I want to write it down on its natural generators. What are the natural generators for SN? 1, 2, the 2 cycle, and 1 up to N, the N cycle. I cannot get a presentation on those 2 generators for the file group which is shorter than O of N. So that's the reason why there is a discrepancy between the bound here and the bound here. And then for exceptional groups, Martin Liebeck and I, who worked on constructive recognition for the exceptional groups, we used the reduced Steinberg-Tietz presentations for the exceptional groups. There's work of John Bray et al. For presentations for sporadic groups, etc. So effectively, we have presentations for all finite simple groups on their standard generators. And so when I go through the process of producing my claimed standard generators, I can now feed them into this presentation and check that they satisfy the relations. That's how I upgrade from Monte Carlo to Las Vegas and remove the possibility of error. Okay, how do we put it all together? We put it all together via an algorithm which is called composition tree. Composition tree owes much of its genesis to work of Charles Lindgren from the end of the 1990s, in which he proposed this as a suitable model. The realization of it took about 20 years of hard work, I can tell you. The algorithm uses geometry and constructive recognition to compute what we call a composition tree for the group. And here's the sort of model of it, where again, I'm back to this representation. I'm thinking of a section of the group, or an intermediate section of the group, H. I'm thinking of having an image I, which is the image under some homomorphism or isomorphism, and I'm thinking of a kernel associated with that, which I've labeled K. And this composition tree, it's a recursive procedure. You start out with the group, you use Aschbacher and other homomorphisms and isomorphisms in order to write down images, kernels. You recursively complete that process, you get down to the bottom. What are the bottom? The bottom are C8, C9 groups, in other words, the groups which are simple or close to simple. And so when we've computed the tree, we can read off what the leaves of the tree are. What are the leaves? The leaves are the composition factors of the group. So once we've computed the tree, we know what the composition factors are, and we know what the order of the group is. So I've identified that I can answer two of the questions which I posed at the beginning of the talk. Okay, much of the development of this happened during 20 years. The final paper on it was written in 2015 with Henrik Barnheim, who was a postdoc here at the time, Derek Holt, Charles, and myself. There's a copy of it available in Magma, which is very widely used. People don't even know that they're using it in the background when you ask questions anymore, because it's become part and parcel of the standard infrastructure. And there's a version of it under development within GAP. Okay, here's a reasonably formal statement of what the output of the algorithm is. The input is just a bunch of matrices which generate the group. What's the output? The output is a composition series, and then standard representation SK for each composition factor, which is GK modulo GK minus 1. Effective maps or effective isomorphisms between the standard copy and the non-standard copy. So that's the output of composition tree. A couple of things to say about it. First of all, I want to upgrade the algorithm from Monte Carlo to Las Vegas. I use the same idea of presentations that I talked about earlier. We know what the presentations of leaves are because we've written them down quite explicitly on standard generators. If we take two leaves, we can move back up to its parent, their common parent, and put together the presentations which we got for the two leaves, come back up to its parent. And then we can repeat that process of working all the way up through the tree to write down a presentation for the group described by the tree. And that's how we produce a presentation for the group defined by the tree, and we check that G satisfies those relations. If it does, all is well, we've got a composition tree for G. So we get a Las Vegas algorithm from that process. I want to say that this is my view of what composition tree is. It's the analog to Schreier-Simms data structure for permutation groups. It gives us, very critically, it gives us an answer to the absolutely fundamental question, which is if I take some X, which is in the parent group of G, so it might lie in GLDQ, and I ask, is X an element of G? If it is, it will say yes, and it will give me a word in the generators for G which evaluates to little x. So that is the absolutely fundamental question which has to be solved from an application point of view. In all applications, you're asking variants of this question, and you absolutely need the word, which is why when I was talking about finding standard generators, I went through the fuss of saying we have to find the standard generators as words in our input generators, because then we can solve problems with respect to the standard generators, but ultimately we have to go back to whatever nasty generating set God or a human being has given us as input to the algorithm. Okay, so that's what we can get from composition tree. I mentioned earlier that back in 1987, Eugene Lux gave us a polynomial time algorithm which exploits the Schreier-Sims approach for the purpose of giving us composition factors for permutation groups. Rather surprisingly, we managed to get the same result for linear groups. In 2021, in a paper of mine with Derek Holt and Charles Leadham Green, we get essentially the same statement. I've phrased it quite formally here because I don't want to mislead people about what we're stating. I'm stating there's a Las Vegas polynomial time algorithm which takes as input the group G. Forget about subject to, come down to availability, to the availability of polynomial time constructive recognition algorithms and short presentations for non-abelian composition factors. If we have those, then we can construct a composition tree for G, and hence we can read off what the composition factors are. Okay, the reason why I phrased it that way is we have some exceptions which I identified, which are 3 families of exceptional groups for which we do not have polynomial time constructive recognition algorithms. We do have short presentations for all non-abelian composition factors, but buried within that are the 3 exceptions. Secondly, I've got, again, subject to the existence of a discrete log oracle, which can solve the discrete log problem, which really arises from SL2Q. I mentioned earlier that many problems about SL2Q cause challenge. One of them I'll be mentioning tomorrow, and it requires the use of discrete log. Factorizing integers of the form q to the I minus 1, that's related to the order problem. Given the matrix, what's its order? I need an ability to factorize q to the I minus 1 in order to answer that question. So that's where those 2 limitations come from, and I see no immediate way of removing those, which is why I hope the computational number theorists will come up with some solution to those hard problems. We've referred them onwards to experts. Okay, so we get polynomial time for the construction. We're making no statement about what the complexity of that process is. In practice, it's amazingly efficient, but from a theoretical point of view, we were just aiming for polynomial time. We were not aiming for a complexity statement. Okay, let me, in the last few minutes, talk about how we can make use of this. How we can make use of this is via the so-called soluble radical model, which is a uniform approach to working with linear groups. So I'm going to flash this up in the last few minutes to tell you that a finite group typically has a nice characteristic series. What are the terms of this nice characteristic series? The most important of it is O infinity, what we call the soluble radical, the largest soluble normal subgroup of the group. And then sitting above that, we've got S star, where S star modulo O infinity is a direct product of non-abelian simple groups. We've got an action of G on the non-abelian simple factors, which gives us a homomorphism into a symmetric group. And then, by virtue of Schreier's conjecture or now theorem, we've got that P modulo S star sits inside a direct product of outer automorphism groups. So we've got a lot of structure present. And back in the 1990s into the 2000s, Derek Holt and John Cannon and their various groups of people collaborating with Magma started using the refinement of this series in order to provide a framework for answering questions about linear groups. And this framework is, first of all, refine O infinity, because you can produce a chief series for the soluble group, so you get a longer one. And then you have a paradigm, which I'm stating here. If you're given a problem, some problems such as write down conjugacy classes, for example, you solve it, first of all, in G modulo O infinity, because it has heavily prescribed structure. And then you lift the information down through the chief factors. Lifting is a well-understood process. It's not a trivial process. There's lots of technicalities about it, but it's well understood. The real issue becomes, can you solve the problem for the class of almost simple groups? I know I've introduced quasi-simple, etc. This is groups almost, they could be quasi-simple groups with automorphisms sitting on top. That's the way of thinking about it. So what I want to do in the last couple of minutes is just mention that some cases where we have essentially got a reduction down to simple or almost simple. And one of these is on conjugacy classes. Very recent work of mine with Giovanni De Franceschi, who was a PhD student here, with Martin Liebeck. We write down, we have algorithms, we write down explicitly solutions for the conjugacy classes in quasi-simple groups. If you're talking about more generally, alternating groups, sporadic groups are easy. There is progress being made on exceptional groups in terms of literally writing down classes within exceptional groups. It's being done by Martin and me at the moment. Constructive recognition now allows you to take information from the classical group or any other natural copy and map it to some other representation. So we can move classes, centralizers, etc., from the nice group across to the nasty group. And the soluble radical model, thanks to work of Alexander Holtke and others, basically wants to know information about almost simple. There's a little gap between quasi-simple and almost simple. That little gap is a big hole, which I would welcome assistance on filling. But suffice to say, we're getting there. And to talk about two other cases, maximal subgroups, there's beautiful work of Bray, Holt, and Ronnie Dougal, where they write down the maximal subgroups in a variety of contexts, including for all finite simple groups up to particular dimensions. Again, we would like to be able to use that to get the information for maximal subgroups in general. Isilo subgroups have been written down for classical groups. There's a small amount done for exceptional groups by Derek Holt and one of his former students. But to tell you that not everything is done, let me mention two hard problems left. One is intersection and one is normalizer. Neither fits very beautifully within the soluble radical model. All of the machinery that we've developed does help a great deal, but it's not the case that we know how to translate it from the almost simple world to the world of an arbitrary finite group. The intersection is, of course, clear. Given two subgroups, can I write down their intersection? Normalizer, I'm given H as a subgroup of G. Can I compute the normalizer within G of H? There is progress made on some of those, but they remain challenging. And in my -1 minute, I'm going to just mention the following, that groups defined over infinite domains. I've been talking exclusively about GFQ. I know there are plenty of people in the audience who regard GFQ as rather trivial. Why do you spend your life worrying about that when there are so many more attractive and challenging questions over infinite domains? So let me mention that we have dabbled in that, and some of the work we're doing is of use in that. Composition tree can be used to study the congruence images of finitely generated linear groups defined over infinite domains. You write down the congruence image over a finite field, and now you use composition tree for the purpose of studying that congruence image. And I've done some work on that with Ala Detenko and Dane Flannery in 2 papers in the 2000s. First of all, we can use it very effectively to decide finiteness. I do not mean by that we write down the finite congruence image and therefore deduce that the group where we were given over the infinite domain is infinite. I mean instead that we take the presentation which we get for the congruence image, we pull that back to the group defined over the infinite domain. And from that, we can make a deduction relatively straightforwardly as to whether or not the group is finite or infinite. If the group is finite, we can write down an isomorphic copy and now use all of the machinery which I've spent the last half an hour extolling in order to solve all problems with the finite copy. And for people who care about finitely generated linear groups, of course, the theorem is that of Tietz from the 1970s, which says to us there's 2 cases. Either you're in the soluble by finite world, or you're in the world where there's a free subgroup contained in your group. We can decide, using presentations from the finite congruence images, which category of Tietz we're in. We can decide that the group is soluble by finite, and then there's a whole host of things you can do, or you find out by default that you're not in that world. You're in the world of the free subgroup. And if you're going to ask me as a question, can we exhibit a free subgroup? We're making progress on exhibiting free subgroups. Many people in the audience care about that question. And let me flag very recent work, much ongoing work by Alan Detenko, Dane Flannery, and Alexander Holpke, dealing with both cases of Tietz alternative. Alexander is here, he's talking later in the week, and I'm sure he'd be delighted to share his insights on that. Okay, good point at which to stop. Thank you very much.
Thank you, and there's an opportunity to ask questions, but we're going to pass around a microphone. Please use the microphone to ask your question so that the people in the overflow room can hear your question, and similarly, there should be a microphone going around in the overflow room so we can hear any of their questions. So if anybody wants to ask a question? Any questions from here? You want to see anybody? Hang on.
Thank you. What a build up to a question. If I randomly chose k elements of GL DQ, can you tell me what probability subgroup I need?
With 99.99%, you will have a copy of GL.
The whole group?
Yeah. I mean, there are results of Dixon dating back to the 1960s, which tell you that two arbitrary permutations within Sn will generate Sn or An. And exactly the same results exist for random. If you take random elements of GL, you will never find something smaller than GL, apart from possibly SL. You might get stuck in SL. So that's a very bad strategy. You need to be much more careful about choosing random elements.
Further questions? One over there.
I just have a little question about this result about presentations for classical groups on standard generators. What is the significance of the number 8?
What is the significance of the number 8? The significance of number 8 is that in the good old days we sat down and tried to choose nice generators which would allow us to solve writing a random element of the group as a word in those generators. There is no inherent significance to 8. It is simply we ended up writing down at most 8. That's essentially it. They're just nice. We could choose those as the developers of the algorithm. We could choose those to say, we want to work with these as our standard generators. Of course, part of what we focus on is that we can find those elements relatively readily. We don't want to choose elements such as 100 elements which we can't find readily. We want to be able to find them readily.
And mostly, do you have exactly 8 in the presentation?
We have exactly 8 for the symplectic group, but fewer for everything else. Like 4 for SL, for example.
Any further questions from here? Any questions from
somebody up there?
See somebody up there?
Sorry, I think this is kind of a stupid question, but is there any combinatorial or computational significance to the fact that the composition trees are like valency 2?
No, I don't think so. I think we're just simply talking about kernel and image, and therefore they automatically end up as having valency 2. No, we have not studied any property of the composition tree other than to prove that it terminates with leaves in polynomial time.
Question over there.
Thanks for your talk. I have maybe a naive question, but could you please answer anyway? So in your slides, you keep using phi and tau, and my understanding is it's because phi doesn't have to be equal to tau inverse for the isomorphisms. So my question is that can you sometimes guarantee that the isomorphism and its inverse are both effective? Or is it a theorem that you can't do that always?
I'm not sure I've understood all the complexity of your question, but suffice to say that we are producing, certainly from a practical and theoretical point of view, we're often producing homomorphisms which are working modulo scalars rather than isomorphisms. Because if you start out with SL, you will not end up with a copy of SL typically. You'll end up with a copy of PSL. And so there is something which I've brushed under the carpet here, which is talking about isomorphisms when in fact I'm talking about surjections onto a group. And all we want to ensure is that we can really go both ways. When I was talking about taking information which we have written down in the nice copy, I really want to be able to take it across to the nasty copy, and I want to be able to go the other way. So I'm very interested in having real machinery which does that. There's lots of technicalities about how you achieve that, but we have not thought about, I mean, there is no theorem that I know of which would say that this is either impossible. I mean, we're exhibiting that it's possible.
Yeah. Thank you.
Okay.
Any questions from the overflow room? Any further questions from here? Well, if not, let's thank Eamonn for a fascinating history and survey.